For general optimization problems, the solution doesn't need to be global optimal, but it is guaranteed to be an optimal solution. However, there are specific case of optimization problem, which is called the convex optimization problem. And for convex optimization problem, then the optimal solution is a global optimal solution. And again, this is by the property that for convex problems or for convex optimization problem, any locally optimal point of a convex problem is global optimal. So that's why as a result, the solution we find is a global optimization problem, global optimal. And in this case, again, similarly, we have f0x. This is the objective function. And again, for the constraint fix, we have convex constraint. We have fi0x smaller or equal than 0, m times such constraints. And all fix should be convex. So in order for the problem to be convex, all the constraints as well as the objective function should be convex. In this case, fix should be convex, and it should be smaller or equal than 0 in order to satisfy the convex property. And again, for equality constraints, in order them to be convex, they need to be equality constraint, linear equality constraints. And that's why we have linear equality constraints is the form of ax equals b. And this is how the convex problem looks like. So this is the general formula. And depending on fix becoming linear, quadratic, or some different form, we'll name the problems, we'll subcategorize the problems into different forms. But overall, this is the convex optimization problem. Convex optimization problem. And again, for many cases, when you first formulate the problem may not turn out to be convex. But then if you reformulate the problem in a different way, then it turns out to be convex. So it's quite a good practice to be able to formulate the problems in convex form. And again, there were some of the problems that we have discussed. And if you look at the convex problem classes, there are several problem classes. One easier problem classes is linear programming. And in linear programming, both the objective as well as constraints are linear, both equality and inequality constraints. So as you see, the objective is in the form of affine function, and both objective and the constraints are in the form of affine function. So this is linear, and since it's linear, it's convex by definition, and as well as linear problems are also concave. The constraints are also concave. So in this case, we have gx smaller or equal than h. So again, this is an affine constraint, linear constraints, and this is why this is convex as well, and convex and linear. And again, last constraint is linear equality constraints, and this is also a linear constraint. And that's why overall the problem is basically a linear programming problem. And in this case, as we have discussed earlier, then the feasible set as polyhedron is a result of intersection of different hyperplanes. So each constraint here, such as, for instance, the inequality constraints, defines basically an hyperplane. And intersection of these hyperplanes, as well as these equality constraints, defines a polyhedron. And in this case, solution is guaranteed to exist on the boundary of this polyhedron. And there are certain methods, such as simplex method is one of them, that basically iterates over these boundary points, the boundary extreme points. And as a result of this smarter iteration, it finds the optimal point. And again, the feasible set is polyhedron, and the resulting problem is a linear programming problem. And again, we are looking for the intersection point that's on the extreme. And this was linear programming problem. And again, different problems can be formulated as linear programming problems. One is L1 norm and L infinity norm minimization. So the first is L infinity norm minimization. So L infinity norm is the basically maximum value for a given vector. And in this case, the problem is we try to minimize the L infinity norm of the variable of a vector, and subject to basically inequality and equality constraints. So in this case, basically both inequality and equality constraints are linear. And in this form, this doesn't look like an LP. However, so we can, since we know that infinity norm is the maximum value for each of them, so we can turn into an LP. So turn into an LP as below. So in this case, instead of basically minimizing the infinity norm of the x variable, we are minimizing a variable called t. And in this case, basically, since this is the norm or the absolute value of the maximum norm of this function, we are adding this constraint. So this constraint basically makes sure that the t that we are getting is, in terms of the absolute value, it's the maximum. And it's bounding both below and the upper of the x by basically t for vector t, and it's multiplied by the one vector. And again, the rest of the constraints here are same. Here we have linear programming constraints that are already defined, smaller or equal, and equality constraints. And this is the constraint that we are looking for here. And we try to minimize the t such that basically for x coordinates, this condition, whereas minus t times vector 1, smaller or equal than x, as well as additional constraint, where x is smaller or equal than t times 1, is satisfied. And in this case, this becomes the L1 norm minimization problem as a form of LP. And again, we have the similar thing for L1 minimization. So for L1 minimization, again, it's basically the sum of the absolute values. So in terms of the L1, so L1 norm of x is equal to xi's absolute value summation from 1 to n. And again, this problem is also can be converted into an LP. So in this case, it's the summation of the TIs, and where TI is the absolute value of XI. And for HXI, the absolute value can be expressed as below, where for each XI, we have minus T is smaller than X, and as well as X is smaller or equal than T. And these are the constraints that's been added. So these are L1 norm, linearization. So we are actually linearizing the L1 norm. Linearization. And other than it, we have basically Gx is smaller or equal than H, as well as AX equal B constraint, which are the original constraints of this L1 norm minimization problem. So this is L1 norm and L0 norm. So another class of problem is basically, these were the examples for a linear programming problem, where they can be formulated as linear programming problem. Another class of problem is linear fractional problem. So in linear fractional programming problem, we are interested in minimizing Cx, Ctx plus d, some affine function eval, divided by some affine, another affine function, which is A transpose x plus f. And these are again subject to basically linear inequality and linear equality constraints. And in this case, the problem is defined such that A transpose x plus f should be greater than 0. So the problem is undefined when it's 0. And in order to minimize, then we assume that this is positive. And the assumption is that basically this division or denominator will not change the sign. And again, this is a quasi-convex problem. So it can be solved by bisection method, where we turn this into a quasi-convex problem, where we are instead minimizing some t, where t will be a function of these division variables. So it will be something like C transpose x plus d should be greater or equal than t times E transpose x plus f. And there will be additional constraints t here, where these constraints are satisfied. And in this case, by using this bisection method, where we are always halving this t, we can solve this problem. But this is a quasi-convex way of formulating and solving the problem. So the problem is also interestingly equivalent to a linear programming problem, as you see here. So instead of basically minimizing C transpose XD divided by E transpose X plus F, the objective here we turn this into a linear objective. So again, this requires a bit proof, but for now, I'm just giving you the result. So in this case, it will be basically we define a new variable called y and z, where in this case, E transpose y plus fz is equal to 1. So in this case, this becomes turned into this constraint by using these y and z. And the constraint above becomes C transpose y plus dz. And similarly, we have gy smaller or equal than hc, and ay is equal to bz. So again, the conversion or passing from this linear fractional problem to linear problem is a bit complicated. But in this case, one thing you need to know is basically linear fractional problems can be formulated as linear problems. And another problem is a quadratic programming problem. So in quadratic programming problem, what we have here is we have this quadratic optimization or the quadratic objective function here. So this is a quadratic optimization problem. Here, P is basically a matrix. And in order this problem to be a convex quadratic problem, then this matrix should be positive semi-definite, so known as PSD, where it has multiple definitions. So as we have discussed before, so for instance, it's a determinant. So let me draw again. So it's determinant of P should be greater or equal than 0. So if P basically has eigenvalues like lambda 1, lambda 2, up to, let's say, lambda n, assume that P is n by n matrix. And then in this case, all of these eigenvalues should be greater or equal than 0. And there are other definitions as well. So in this case, but the main definition is for any vector x, x transpose P times x is basically greater or equal than 0. So in this case, for any vector x, the multiplication of these transpose of this vector with this matrix and the vector itself should be greater than 0. In this case, once P satisfies these conditions, then this is known as a convex quadratic problem. So this satisfies the convexity. And again, in addition to the quadratic objective, we still have linear objectives here. And everything else is affine constraints. And again, the constraints defines a polyhedron as in the linear programming problem. So here is the polyhedron, which defines a set, basically the feasible solution set defined by this polyhedron. And again, we are interested in the boundary point, which basically gives us the maximum value in terms of these objectives. And in this case, X star here corresponds to the one which has the maximum point or the maximum objective value. So this is convex quadratic program. Another type of the program is quadratically constrained quadratic program. And again, the difference here is that the constraints or the inequality constraint is also quadratic, as you see here. And again, the inequality constraint is not affine, but it's quadratic right now. And it's 1/2 times x transpose pi times x plus qi transpose x plus ri smaller or equal than 0. And in this case, this is convex. In order this to be convex, then pi's, basically the quadratic or the matrix pi that gives the quadratic property should be again positive semi-definite. And in order for this problem to be basically convex, all the matrices here, starting from the P0 in the objective, and as well as the PIs, P1 up to the PM in the constraints, should be convex. And in this case, again, the problem is convex and optimal solution can be found. And a different problem class is basically a more general problem class than quadratically constrained quadratic problem. And the linear problems that we have seen so far is basically second order cone programming. And in the second order cone programming, and the objective is a linear objective, which is an affine objective. And the constraints are basically second order cone constraints. And the cone comes from the fact that we are using the norm of the affine function. And that's why this is called the second order cone constraints. So in this case, we have this affine function here, the norm of the affine function, AI times X plus BI, and this is its norm, and assume that this is the second norm, should be smaller or equal than some another affine function, Ci transpose times X times DI. And all constraints should be like this. All inequality constraints should be in this second order cone form. And then we have Fx equals G, which is the equality constraint. And again, where basically this is a generalization of this problem. So in this case, for instance, if Ci is 0, then in this case there will be only D, and we can take basically the square of both sides and turn this into a quadratic constraint problem by taking the square when Ci is 0 by taking square of both sides, then square of both sides, we can turn this into a quadratically constrained quadratic problem. And again, second order problem is more general than both quadratically constrained quadratic problem as well as LP. And the last problem is a semi-definite programming problem. These are all the classes that belong to the convex problem, and they are becoming more and more complex. So the first problem we have seen, linear programming, was the easiest one. Then we have seen linear fractional programming. Then we have seen quadratic programming, quadratically constrained programming, second order cone programming. And lastly, we'll now see the semi-definite programming class, which is again convex. And in second order semi-definite programming class, we have this matrix inequality constraints. So in this case, the objective is again linear. We have this C transpose times X. But however, instead of the numbers, now the constraints are in the form of matrix. And this is called the linear matrix inequality. And this abbreviation is LMI. And in this case, we have a linear objective and linear matrix inequality constraints. And in this case, all these Fi, F2, Fn are basically the constraints, matrix constraints, and X is the variable. So combination of these matrices should be smaller or equal than some matrix G. And the smaller or equal than, again, defines in terms of positive semi-definite. So again, G minus all these constraints should be greater or equal than 0, meaning that the resulting matrix where G minus XF1, again, XF0 up to basically XFN is ... minus XNFN. This should be greater or equal than 0, meaning that this matrix, this resulting matrix, should be positive semi-definite, which is again related to the eigenvalues as well as its determinant. So this is semi-definite programming problem. And again, different problems can be turned into semi-definite problem because semi-definite programming is a more general case of this problem. So for instance, if we have a matrix and we try to minimize its eigenvalue, that's also related to the semi-definite problem, a semi-definite programming problem. And again, lastly, so when we have multi-criteria, so up to now, we only have single objective function. And in the single objective function, so basically the optimization was relatively trivial. When we had multiple objective functions, assume that our F0x is made up of Q different objectives, where from F1x up to the Fqx, then the question is, how can we define the optimization problem? How can we define the optimization problems in the forms that we have seen? So that's the question. That's the question that we are interested in. And in this case, one way to define is basically combine the objectives by using different scalars into a single objective function. So there will be a bunch of Pareto optimal solutions. So for instance, for F10x, there will be points, which is maximum F10, F1x, but not optimal F2x. And similarly, there will be some solutions that will be optimal in terms of F2x, but not optimal in terms of the other objective functions. And the resulting solutions or the resulting objectives, instead of single objective function or the single optimal objective value, they define set of optimal points. And these are called Pareto optimal points. So in order to come up with a single value from the Pareto optimal points, we minimize the positive weighted sum of these objective functions. So for instance, we multiply the objective functions f1x and f1x with lambda 1, and for instance, fqx to lambda q's. So all objective values are multiplied by scalars, and this becomes the resulting objective function. So for instance, regularized least squares is an example. So in this case, we have this basically the matrix. And in this regularized least square, we have the least square problem, which is defined as ax minus b's square. So it's basically the second norm's quadratic function of this ax minus b. So given the constraints ax, we are interested in basically x values that tries to equalize the multiplication as close as possible to some right-hand value b. So this is the least square value. And linear regularized version, we are also trying to minimize the norm of the solution. And in this case, we have two objective functions. Well, this is for least squares, linear least squares. And in this case, second norm. So this is the objective function. And in this case, for this type of problem, one trick is basically multiply the second norm by some, again, the coefficient, which is gamma here, and then solve for the single optimal objective value. So this is an example of how we can scalarize the multi-criteria problems. In this case, there are two multi-criterias. So again, this is basically the convex optimization. So again, for those of you interested in, you can take a look at look at the different functions. So in this case, there was a chat question, so I just noticed. Sorry for noticing this late. So if you can ask in speech, that will be better. So the affine function is for a given vector. So it's ax, a transpose xb. So it's basically a linear form plus some constants. So it's x vector is scalarized or some scalarized by some vector a transpose, and a constant b is added as a result. So this is basically an affine function for vector, affine function for vector. And for matrices, we have, again, A transpose X. So they will be a matrix, A transpose plus B. That will also be basically an affine function. And again, both are affine functions. So you can think this in terms of linear functions. That's what they are same of. And in terms of references, you can look at the convex optimization book by Stephen Boyd. So this book is available freely. So this will be a quite good reference on basically the convex optimization problems.